Number 14 is about turtle populations. So at time t equals 0, some turtles are released into a wetland. When t equals 4 years, the biologist goes out and estimates that there are about 300 turtles in the wetland. 3 years later, the biologist estimates that there are about 450 turtles. The p represents the size of the turtle population in year t. So we're going to create a linear model, and we'll interpret the slope and intercept in terms of the problem. And then we'll create an exponential model and interpret the parameters in context of the problem as well. Okay, and then once you're done with that, I'd like you to give part C a try. So in year t equals 12, the biologist estimates that there are 900 turtles in the wetland. Which model seems like the best fit for the first 12 years? So give some evidence or proof to support your decision. So we've practiced this part, so I feel pretty confident that you can conquer this, and I'd like you to give this one some thought. So go ahead and pause that video and give those a try, and I'll give you your 2 points up here before you pause that. So this will be 4, 300, and then 3 years later gives us 7, 450. All right, so those are your 2 points. Go ahead and give that a pause. All right, so let's see if we came to about the same conclusions here. My slope is going to be 450 minus 300 over 7 minus 4, which gives me 50. And then I don't have my intercept, so I'll use point slope form with the 4 and the 300. So I have p minus 300 is equal to 50 times parentheses t minus 4. So p is 50t minus 200 plus 300. So 50t plus 100. And then to interpret this in context, my slope is 50. So my population increases, because that's positive, by 50 turtles per year. And then my intercept is this number 100. And that's my initial turtle population. So it's 100 turtles to start with. All right, so that gives us our linear model. And then our exponential model, we'll start by setting up that ratio. We have AB to the 7th is equal to 450 over AB to the 4th, which is 300. So it gives me B cubed is equal to 1.5. Okay, and then if I take the cube root of B, I'm going to get approximately 1.14. And then I need to find A, so I'll use this part here. So I have A times 1.14 to the 4th equals 300. So A is going to be roughly 178. My equation is going to look like P is 178 times 1.14 raised to the T. And to interpret that in context, I'll start by interpreting A. My A is 178. That is 178 turtles to start. That's my initial population. And then I have B is equal to 1.14, which means that R is equal to 0.14. So remember the relationship there is that B is equal to 1 plus R. Okay, so my R is 0.14 or 14%. And so my turtle population increases by 14% per year. All right, and then part C. So we have these 2 models, and we want to know which one seems like the better fit. So we know right now that both of these models will give us these 2 points. What we're hoping for is that there will be a model, one of these 2 will be close to giving us 12, 900. Right, so to determine that, we're going to plug 12 into both equations. I'll start with the linear one. P of 12 is equal to 50 times 12 plus 100. So it gives me 600 plus 100, or 700 turtles. So not great, but not bad either. I mean, 700 isn't too far away from 900. Let's see how the exponential model fits. So P of 12 is 178 times 1.14 to the 12th power. If we punch that in our trusty calculator, we get about 858 turtles, which is a whole lot closer to this 900. So for these first 12 years, I would say that the exponential model is a better fit. Okay. All right, and picture-wise, what we're looking at here, just section 4.3 will be about graphs of exponentials, but let's just touch on that really quickly here. So this is my linear model. I get that nice straight line. My exponential model, so this one started at 100. This one's going to start a little higher at 178. What's going to happen is it's going to curve upward like this. Okay, so that's kind of the difference between the graphs of those two.